So we ended the last lecture talking about section 3, perception, and we just went over some of the big ideas, but we ended here with a very specific focus for today's lecture, and that was the concept of depth perception. So at this point, you should have watched the film, the YouTube clips about the visual cliff and the tests they've done with babies over the years. Famous historical experiment in psychology, but it has been replicated many times over since then. Not only did we learn that it's just really cute to work with babies as you watch that video clip, but one of the other things that the experiments that have been done with the visual clip tell us is just a little bit about how depth perception, perception in general, but in this case, depth perception is a learned activity. The babies at first will crawl right off of that cliff with no concerns about it whatsoever. They have to learn that that's dangerous, and then eventually they can determine whether or not they want to walk off that because they can see the depth below the glass floor. So a couple cool things there. Just use that as a way to introduce the concept. So let's talk a little bit more about depth perception. So what we're going to talk about today are the external cues and internal cues of depth perception. So I have a list of different external cues here of depth perception. I'm going to explain each one, and then I'm going to give you some visual image that will help you understand how this works. This isn't rocket science, this stuff makes sense, but what's crazy about it is all of these things that I'm going to go over right here, 1, 2, 3, 4, 5, 6 of them, are things that your brain is doing, my brain, our brains are doing all the time without us even knowing it. This is a subconscious process that our brain is going through all the time. So let's start with size. Very simply, our brain knows that something that is larger is closer than something that is smaller. Big is closer. That's all you need to know. For example, if we were to look at this and our brain sees these two books sitting on this table here, one of those books, even though they are actually the same size, we'll get the constancy later, but one of those books is clearly larger than the other. Our brain can see that, and that's just one of the cues that it uses to understand that that book on the right is closer to us than the book on the left. A second cue that our brain uses is something called interposition. The rule here is that objects that we can see in their entirety are closer than objects that we can't completely see. What do we mean by that? Well, your brain is always processing things like this. Obviously, and this is a two-dimensional image here too, but our brain can perceive which one of these shapes is the closest and which one is the furthest away based on their interposition. The only one that we can see in its entirety is the circle. We know, our brain knows that that circle has to be closer to us than those other shapes. Or we do that all the time when we're looking down busy streets, if we're looking down the hallway, all that kind of stuff. We can use interposition to determine depth. A third cue that our brain uses, again, subconsciously, without us even knowing it, is shadows. Now this one's harder to fully explain other than just to say that our brain is always evaluating the shadows that we see. We don't even realize that we're seeing these shadows, but our brain is always looking at the way shadows are casting around us. It is evaluating how big or small the shadow is, the length of it, is it skinny or fat? Is it dark or light? All kinds of different things. And with shadows, our brain also can help or can also determine depth. So this picture here doesn't necessarily explain it, but based on where these shadows are falling just in this visual image, our brain can measure certain things about the depth of these different spheres, and even their shape and some other things too. All right. Texture density gradient, that's an interesting thing. Simply put, objects that are closer to us, we see with greater detail. The texture of them is sharper and the detail is clearer. Things that are further away from us, they start to lose their sharpness. I don't know on this video how well you can see that picture that I chose, but you see a girl holding a softball out in front of her. And here it's just it's a tool that you can utilize when you use camera lenses, but our brain is doing this as well when the lens of our eye is doing this. That hand in softball is really sharp and you can see it perfectly. The girl's face behind it, which is further away, is blurry and not as sharp. So that's something we call texture density gradient. Okay, your brain's not done. There's more that your brain is processing, like atmospheric perspective. The way the definition is, it sounds kind of weird, but by definition it says this is when we use pollution in the air to detect distance. When we say pollution, really anything that is in the atmosphere. Any of the molecules that are in the air that we're looking at can help us determine depth if we see things like this. When you look at things that are far away, the contaminants that are in the atmosphere will make those images harder to see. They won't be as sharp, they won't be as focused. That's when you see off in the distance, each of these mountain ranges just gets a little bit mistier and cloudier. Or have you ever been outside on a hot day and you're looking down the street, and way at the end of the street it just looks like there's like the street's wavy, it's almost like there's fumes coming off. Well, because of the heat, there are things in the atmosphere that we can recognize, and when you see that, it tells your brain that that's far. If you look at the concrete right in front of you, it's not shimmering, you don't see that steam coming up, right? So that's something we call atmospheric perspective. And there's still one more. We also use linear perspective. This rule states that parallel lines will appear to get closer the farther they are away from us. Now we know that parallel lines never get closer to each other. That's part of the definition of something being parallel. They will never get closer. They'll never touch one another. But when parallel lines go further and further away from us, they do have the appearance as though they're going to touch and that they are coming together. Hey, whoa, excuse me. Something got me. Something in the atmosphere. So here we see the classic image of straight parallel railroad tracks heading away from us. As you look at those railroad tracks off in the distance, clearly the distance between these two rails right here is the identical distance as it is right here and the same distance right here. But visually speaking, it looks like that distance is getting closer and closer and closer, and the tracks are coming together. So our brain uses that rule to understand that the tracks that seem close together are further away from us. Holy cow. So our brain is using all of these things all the time. We don't even know it. And because of that, though, we are able to judge distances and depths in the world that we're interacting with. Pretty cool stuff. Guess what? Your brain does a few more things than just these 6. Let's add a few internal cues of depth perception. There are 3 internal cues of depth perception. These are more like biological things that are happening with our body, and less just the way the physical world, the laws and rules of the physical world are helping the brain. One thing that our eyes physically do is something called convergence. If you take an object, your pen or a pencil, or even just your thumb or your finger, and you hold it out far away from you, and you start to bring it closer, you can't really even tell this unless you watch somebody else do this, but you should be able to see that my eyes are turning inward towards the object. When our eyes do that, when they are drawn to do that, this convergence as it's called, our brain knows that that thing that we're converging our eyes on is close to us. When it gets far away from us, our eyes will separate again. Just another internal cue that our brain uses to understand when something is close and something is far. These other 2 are going to be very difficult for me to demonstrate. You're going to have to kind of do this on your own, but see if it works. Motion parallax is oftentimes hard for people to fully grasp, and even whenever you do this demonstration that I'll give you to do, it may not make sense to you, but motion parallax is the apparent movement of objects that are stationary, that are not moving, but they look like they're moving when we move. So this isn't going to make any sense to you, but I'm going to look at this controller sitting on the desk. I don't know if you can see that. All right, no, I'm going to look at my little bear up here at the top. And if I just stand here and I don't move, and I'm looking at that bear, it's not moving. Neither am I, and it's stationary. I know that. But as soon as I start to move, that bear, appears to be moving. Like right now, it's moving to the right quickly, then it stops. As soon as I move, it changes its position in my visual field. And it literally looks like it's moving if I really concentrate on that idea. You don't recognize this, and you're going to try this at home right now. Hopefully you're trying it. And it may not be, you may not fully get the impact of it because we're just so used to, like I'm moving right now and I can see things on the other side of my room. They start moving as soon as I step and walk. We're so used to it because it's happening all the time when we're in motion and our brain is just processing it that it's hard for us even to replicate it when we're trying to see it. But that is something called motion parallax. Give it a shot, see if it works. This third and final cue of depth perception, you will be able to make this one work. Now you're gonna have to go outside and take a car ride. Hopefully you're not driving. I don't want you to try this while you're driving. You gotta do this as a passenger. Maybe on the bus ride home from school, or if you get in a car, go out for dinner tonight or something, I want you to try this. Relative motion occurs when we are in motion, when we are moving. Objects that are close to us logically move in the opposite direction that we're moving. So for example, if you do get in a car and you sit and look out the passenger side window as you're flying down 79 at 70 miles an hour, and you look at that guardrail that is real close to the side of the road, which direction is it moving in? It's going this way. It's going behind you, right, as you're going forward. That makes sense. But what I want you to do is I want you to look at that guardrail. You'll see it, it's just flying, especially if it's really close. It's just flying right past you. But then just adjust your gaze, look past that guardrail, and look at the hillsides in the horizon or the tree line off in the distance. Guess what direction that's moving? That far object is actually moving in the same direction as you. So you're gonna have close things flying by this way and then far things slowly moving with you. It's called motion or relative motion. Give it a shot. Again, not if you're driving. Keep your eyes on the road if you're driving. But if you're a passenger, see if you can recognize this phenomenon. Your brain recognizes it all the time, and it's always processing it, and it knows that that guardrail is close, and those trees at the other end of the field are far away. All right. So there we have a little bit about the different cues of depth perception. And I want to end with one final vocabulary term, like inundating you with vocabulary. Don't worry, when we're done with this, you're going to I have a worksheet in there for you to do a little review of this, to go back through these images and these vocabulary terms. But one more, and that is constancy. Constancy occurs because we can perceive things the same way all the time. The shape, size, brightness, color, all that kind of stuff of any object that we are familiar with, we will perceive it the same way no matter what the circumstances or the conditions. So for example, if I see you and you're 5'7" and I see you standing right next to me out in the hallway, I can kind of get that you're around 5'7". I will perceive your actual height accurately because my eyes are doing all this other stuff, right? And my brain's doing it. Well, guess what? If an hour from now, after a second period or something, I see you all the way down the hallway, down near the band room or something down there, you really are going to look like I could pinch you in my fingers like this, right? But I still know and understand and perceive that you are 5'7" tall, not that you are 1 inch big. Our brain is able to process that, and that's something that we call constancy. Now, as is the case with a lot of this stuff about perception in general, depth perception in particular, we have to interact with our world and have experiences where we learn how to do all these things. Because I have experience with you, I know you, I'm familiar with you, I've seen you every day in class, I can perceive that you're 5'7" tall, whether you're standing next to me or if you're all the way down the other end of the hallway. All right. And there we have a little bit about depth perception. We're going to stop there for today. What you're going to do is, well, just follow directions on Schoology, and there should be a worksheet for you to practice some of this. All right, have a great day.